This video is about using the Mclaren expansion. This is what it is at the top there. F of x is equal to f of 0 plus x times f dash of 0 plus x squared over 2 factorial times f dash dash of 0, and that pattern continues. So that's what the formula is. You can see there's some common examples below it. You can see that e to the x is equal to 1 plus x squared over 2 factorial, and so on. You can see ln of 1 plus x is x minus x squared over 2 plus x cubed over 3, and so on. And there's the expansion for sine x and cos x at the bottom. Now, there's a whole host of reasons about why we might want to write a function as a series of x terms, as a polynomial. I'm not going to go over those reasons in this video, but do ask me in our lesson on this to go over that with you. I just want to show you how you can use the formula at the top there to generate these series as you for yourselves. Obviously, they are series. There are as many terms as you want to include for this. Obviously, the more terms you include, the more accurate your approximation is going to be. Okay, so first of all, let's do the e to the x function. Let's find a series expansion for e to the x. So if our function is e to the x, then f of 0 is e to the power 0, which is 1. When we differentiate the function, we get e to the x. Nothing changes. Therefore, f dash of 0 is still e to the 0, which is 1. And if we keep going, f dash dash of x, that's still, if I differentiate for the second time, it's still going to be e to the x. So therefore, f dash dash of 0 is still going to be e to the 0, which is still going to be 1, and so on. So plugging these results now into our series expansion at the top, into this. Our f of x, our e to the x, is going to be equal to f of 0, which is 1, plus x times f dash of 0, so x times 1, plus x squared over 2 factorial, two times 1 is just 2, and that's going to be multiplied by f dash dash of 0, which is 1. And that pattern's going to continue. So the next term would be x cubed over 3 factorial, so 3 times 2 times 1, multiplied by f dash 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 of 0, which is going to be 1 again in this case. The next term after that would be x to the power 4 over 4 factorial, so 4 times 3 times 2, multiplied by f dash 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 of 0, which again is going to be 1. So this is our Mclaren series expansion for e to the power x. Next, we're going to get the Mclaren series for cos. It's slightly more complicated now, but not hugely. Still going to do the same thing. If f of x is equal to cos of x, then f of 0, substituting 0 into that, cos of 0 is 1. Differentiating cos gives us minus sine. Substituting 0 into that, well, sine of 0 is 0. Differentiating for the second time. So sine differentiates to be cos. So it'd be minus cos, because it's minus sine. Substituting 0 into that, we've got minus cos of 0, so minus cos of 0. Cos of 0 is 1, so minus 1. Differentiating for the third time, cos differentiates to be minus sine, so minus cos is going to differentiate to be sine. Substituting 0 into that gives 0. And then we'll do one last one. Differentiating for the fourth time, sine differentiates to be cos. Substituting 0 into that will give us 1. And actually, you can probably see at this point, this is just going to oscillate now. It's just going to cycle between these things because we're back where we started from. Anyway, let's apply all of what we've just seen to this rule at the top here, to the Mclaren expansion. So our f of x is cos, and that's equal to f of 0, which was 1, plus x times f dash of 0, which was 0, plus x squared over 2 factorial times f dash dash of 0, which is minus 1, plus x cubed over 3 factorial times f dash 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 of 0, which is 0, plus x to the power 4 over 4 factorial times f of f dash 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 of 0, and so on, which will simplify to be 1 minus x squared over 2 plus x squared, x to the power 4 over 24, and so on. So this is our Mclaren expansion for cos of x. So that's all it is. That's all there is to it. This is the key formula to remember and the key pattern to learn. This is how you can organise yourself so you don't get too confused. It allows you to take a function that could be considered complicated, but like cos or exponential or sine or a logarithm, and allows you to express it in terms of nice simple polynomials in terms of powers of x. You may, for example, notice the bit at the front. You should spot something here. If I just actually highlight just this bit here, you should recognise that from your small angle approximations that we did in regular maths. Because if x is small, then that allows you to ignore all of these other high power terms. So the power 4, if x is small, x to the power 4 is going to be tiny. X to the power 6, the next term in this sequence, would be minuscule, and so on. So you could, if x is small, you can ignore all of those other terms, and hence we've got another, probably more efficient way of deriving your small angular approximations here. There we go.